now that we've learned a little bit more about the Maclaurin series, we're going to talk about operations within the Maclaurin series. So today we're going to talk about composite functions as well as addition and subtraction of the Maclaurin series. Later we'll talk about multiplication and division, but for now we're going to start with just composition and addition and subtraction. So starting off with composition of functions, we have a standard list of common Maclaurin series that's useful to us, and remember that's provided to you in your IB formula booklet. And we can use that to generate infinite series of representations using composite functions. Now just a note, we talked about convergence previously. An infinite series will only converge if the interval of convergence of the original Maclaurin series is obeyed, and then an infinite series generated is only itself a Maclaurin series if it is a polynomial. So we're just going to jump right on into a composition of functions. So first off, it tells us use the Maclaurin series that 1 over 2 plus x is given to us in summation form, and we want to use that to find the Maclaurin series for 2 minus x squared. Now just a reminder, the Maclaurin series, the whole purpose of it is it's a polynomial expansion that will allow us to look at complicated functions in polynomial format. Now, in the functions that were given in this example, these are not too earth-shattering, but higher up in the levels of mathematics, the higher you go, you might see more complicated functions where a Maclaurin series is actually helpful to us. It is actually helpful to see what that looks like. So I'm going to start by just rewriting our Maclaurin series that is given to us. And again, this represents a polynomial approximation of the curve 2 plus x. And then we have times x to the k. Now we want to use that to approximate, find the Maclaurin series for 1 over 2 minus x squared. Now I want you to notice the only difference we have right here is this term right here. So what we're going to do is take every single x that we see in our summation and we're going to replace it with a negative x squared. So we have k equals 0 to infinity, negative 1 to the k power, 2 to the k plus 1 power, and then I'm replacing my x squared with negative x squared to the k power. Now I don't want to just leave it like this. I want to simplify my answer as much as possible. We know this. So what I'm going to do is I'm going to separate my negative x squared to the k power a little bit. So I'm going to rewrite this, k equals 0 to infinity, negative 1k over 2k to the 1 power. I'm going to rewrite this term as negative 1 to the k power and x squared to the k power. We know that's actually what's happening here. We know we can separate those terms. And then lastly, negative 1 to the k power, 2 to the k plus 1 power, negative 1k to the power, and I'm going to rewrite this as x to the 2k power. Now you may notice here I have 2 negative 1 to the k's power. Remember, 2 negatives cancel each other out. If I want to be super explicit about this, I can write this as negative 1 to the 2k power. That's going to verify that our numerator, or my exponent, is always going to be even, making this sum always positive. So since this is always positive, I can drop it. It's always positive, so I can go ahead and drop this component. So I'm just left with x to the 2k over 2 to the k plus 1 power. So this is the fully simplified version of that Maclaurin series. So again, this is representing 1 over 2 minus x squared. If I were to multiply or add all these terms together, that would give me the polynomial approximation. Now if we go back to the original problem, it says write down the terms of the series up to x to the 6. So we're going to actually see what this looks like written in polynomial format. So if I plug in k equals 0, that's where I'm supposed to start. I'm going to have 2 to the 2 times 0 over 2 to the 0 plus 1 or this is x actually, x to the 2 to the 0 power plus 2. I'm going to keep going, so now I'm going to plug in 1. X to the 2 times 1 power over 2, 1 plus 1. I know that this is going to give me x squared. I need to go to x to the 6th, so I need to keep going. So x to the 2 times 2 power, that's going to give me a power of 4. I need to keep going. And then lastly, I'm going to have 2 to the 3 power, and then 2 to the 3 plus 1. So when I go to simplify this, I'm going to have 1 over 2 plus x squared over 4 plus x to the 4th over 8, and then plus x to the 6th over 16. I know that this is going to continue. I know that the summation is going to continue because it goes all the way up to infinity. But here the problem is just asking me to go up until the x to the 6th term, so I have done that, and now I am finished. Moving on to the next problem, I'm going to just move over my work a little bit so I have enough room for my next problem. So that k is supposed to go here. I'm going to go into my next problem. We're only going to go through parts A and B together. If you're interested in looking at parts C and D, feel free to go into your textbook and click on that self-tutor button. That'll really explain parts C and D to you. But the purpose of these lessons is really to just give you the basic information, give you the information that you would need to solve a problem given to you on the IB exam. And because of that, I'm only going to go through parts A and B. Again, if you want to continue, you can absolutely go check out parts C and D, but I'm just going to go through parts A and B. So we're going to use the Maclaurin series expansion of e to the x to write down the expansions of 3 new components using our composition of functions. Now remember, in your IB formula book, you get e to the x, and then you have this summation. This is already given to you. Remember, everything that you do on your IB exam, there's going to be some sort of component where you are using the formula booklet. So if you are not, keep looking. There's going to be something to help you out. So this is just a little bit of what this looks like. And again, this is given to you in your IB formula booklet. So for part A, we want to use this expansion to help us. Part I, we want e to the 2x power. So writing in my summation form, if you remember from the last problem, all we did was change the x. Here, my exponent is 2x, so every time I see an x, I'm going to replace that with a 2x. Nothing else changes. My k's stay exactly the same. So this is going to be 2x to the k power over k factorial. And just to write this out a little bit, this is going to be 1 plus 2x plus 4x squared over 2 factorial plus 8x cubed over 3 factorial. And again, this is going to continue. So that's part I. Part 2, I want e to the 4x, so I'm going to do the same thing. So e to the 4x is equal to, I'm still using that Maclaurin series expansion. The only thing I'm changing is this 4x term. What this is going to look like when I add all these terms together, I have 1 plus 4x plus 16x squared over 2 factorial plus 64x cubed over 3 factorial, and this is going to continue. The last thing I need to do is find e to the nx power. So this is just a general term, but the same process is still going to hold true. I'm just replacing this inside component with nx. Now, even when I multiply or when I expand this out, it's still going to be the same thing. I can see a pattern happening in parts 1 and 2. So I'm going to have 1 plus nx. My numerator is going to be nx quantity squared over 2 factorial, and I see that pattern repeating. This is going to be 3 over 3 factorial, and this is continuing. So I have that general rule. Now, if I go back to part B, I want to use the Maclaurin series expansion for cosine to find the composition, find the first 2 non-zero terms of the Maclaurin series expansion of e to the cosine x. So now, again, I have the cosine x expansion given to me in my IB formula booklet. So this is 1 minus x squared over 2 factorial plus x to the 4th, this is part B again, x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And this is going to continue every single time. I don't have this one written in summation form, but this is just written out what it would look like. All right, now I need to use this to approximate what cosine e to the x would be. So we're going to do the same process that we did last time. Previously I saw an x, now I'm going to have an e to the x. So I'm going to replace everything that I see. So 1 minus e to the x squared, my x is in my exponent, 2 factorial plus e to the x to the 4th power over 4 factorial, e to the x to the 6th power over 6 factorial, and again this pattern is going to continue. Now I want this ideally to be in summation form, so I'm going to do whatever I can to get this into summation form. So the first thing that I'm going to do is simplify my numerators just a little bit. So I'm going to have 2x over 2 factorial plus e to the 4x over 4 factorial, and then e to the 6x over 6 factorial. Now just to give you a little bit of a heads up to where I'm going, I don't really have a good summation version for cosine. I mean, I do in my formula booklet, but written on this paper I don't right now. But I do have some summations for x e to the x squared, or I'm sorry, e to the 2x, e to the 4x, and e to the nx. So I'm going to use what I found in part A to help me out in part B. So from part A, I know that e to the 2x, I'm going to rewrite this as 1 over 2 factorial. I know that e to the 2x is 1 plus 2x plus 4x squared over 2 factorial, and this pattern is going to continue. So again, this is coming from e to the 2x right here. And I'm going to do the same thing with the rest of my terms. So I'm going to have plus 1 over 4 factorial. I know that my e to the 4x is going to look like this. So I'm going to have 1 plus 4x plus 16x squared over 2 factorial. And again, I don't need to write all of these terms. The pattern is going to continue every single time, but this comes from here. And now what I'm going to do is I'm going to see if I can come up with a general rule for what's happening here. So this is going to continue, and I'm going to try and see if I can come up with that rule. Now I know I have something out front, and then I have that it's being multiplied by something. So what I'm going to do is I'm going to see if I can write a rule for what's happening with my coefficients out front. So I'm noticing that my signs are alternating. I'm going from positive to negative to positive to negative. So I'm going to represent that as -1 to the k power. I know that on my second term, I have a negative number. On my third term, I have a positive number. So I'm going to write this to represent that oscillating factor. And then my denominator is going to be 2k factorial. So I have 2 factorial, 4 factorial, 6 factorial. I notice that pattern happening every single time. Now for what's on the inside, I'm noticing that I have 1, and then I've got my 2kx, and then I've got a 2k squared over x, or 2k x squared over 2 factorial, and I see this pattern continuing. Alright, so moving on to the next part, going back to the original problem, it says find the first 2 non-zero terms. So I already know that this is going to be my first term. I know my first term is 1. So we're going to make kind of a switching gear. So this is what's happening right now. This is my general term. If I want the full expansion, this is what I'm going to do. But I only want the first 2 non-zero terms. So in that case, cosine e to the x, I know that my first term is 1. That's fine. Now my next term, I know if I distribute this, let me change this color. If I distribute this in, I'm going to get another constant. So I'm going to have 1 plus some sort of constant. Those are going to go together. So that becomes my first term. It's not until I multiply in here where I'm going to get my first x, and that creates, I want an addition there, my second term. So I need to figure out exactly what those first and second terms are. So what I'm going to do is I'm going to use that summation that we kind of worked with previously and allow that to help me figure out the pattern for these first 2 non-zero terms. So what I'm going to do is I'm going to use a summation here. So I'm going to start at 0 and go to infinity. That's what we always, actually just kidding, starting at 1 because I already have my 1 here. This is oscillating in sign, going from positive to negative, and then I have my 2k factorial. This is the same pattern that we developed in this part right here. Now I'm going to do the same thing with my secondary term. I'm going to start at 1, and I'm going to go to infinity, and I know that the rule, I can develop a rule for this right here, which is actually given to us is given to us. So I'm going to write this as -1 to the k power 2 times k over 2k factorial, because I still have this term multiplied by this one. So I'm putting those two components together. All right, so now I'm just going to simplify a little bit more, and then I'll be all finished. So I'm going to have my 1 plus, this term I can't really do a whole lot with, so I'm just going to leave this as is. But this next term I can simplify quite a bit more. So just a reminder, whenever we have factorials, we can do some simplification with this. So if I have 6 factorial, and remember this is 6 times 5 times 4 times 3 times 2 times 1. So let's say I have 6 over 6 factorial. That means I have 6 over all of this. Notice how my 6's cancel. So I'm left with 1 over, and I'm left with 5 factorial. So to get from here to here, I'm just subtracting 1. So I'm going to use that same process with my 2k. So again, I'm going to start at 1, go all the way up to infinity, -1 to the k power. I'm going to be focusing on these two terms right now, so I want to cancel that. So this is going to leave me with 2k minus 1 factorial, and then I still have that x in there. So this is what my first 2 non-zero terms are going to look like. Again, this is a constant. There's no x's here, so this is just my constant. So these two terms are going to simplify to be one term, and now this is my x term. So that's what's happening in this equation. I do have some additional practice problems in our notes, so you can go ahead and look at those, and I have the keys posted for you. But I want to go back up and talk about addition and subtraction real quick. Obviously, our Maclaurin series is representing polynomials. Yes, we can add and subtract polynomials. We did that in linear algebra. We've done that in several other instances. So it doesn't seem unreasonable that we can add and subtract Maclaurin series as well. And again, that interval of convergence is going to be very important here. I actually don't have an example for us to go through for addition and subtraction, but you can go ahead and look on your notes online to see some homework problems that model addition and subtraction of Maclaurin series.